All right, hello class. Welcome back to part B of this lecture. So in this part, we're going to examine the one missing piece of our analysis of the two-body problem in 2 dimensions. And that is, or at least the part related to propagating the orbit in time. And that is the conversion between mean anomaly and eccentric anomaly, where, remember, our goal here is to convert from t to f and hence to r and v, where t we were able to get to mean anomaly through the mean motion. For mean anomaly, we have the Kepler equation, which is not written on this board, but I believe it's E sine, or is it cosine? I should double check that. Sine, yes. Is it plus or minus? Minus. Made a little typo there. Minus E. And of course, from E to true anomaly, we have those conversion factors, so that's all taken care of. So as of now, we've shown how to get from E to M. That's fairly easy, just plug in E. But then the converse is a little bit more difficult, how to solve for E given M. And that's the topic of the remaining few slides in this class, in this lecture. Right, so here's the formula for this conversion. There's the formula for this conversion. And there's the formula for that conversion. So now we'll talk about how to go this direction, M to E. So on its surface, it's a relatively straightforward problem, right? We want to invert this formula, right? Sadly, however, there's no analytic inversion for this formula. And this wouldn't be such a problem. We could sort of tabulate numbers, as we do for sine and cosine. Remember, sine E, cosine E, right? Because there's no analytic formula for those either, where we could just create a table, and this is E, and this is sine E. And this, of course, we have tables for that's how they calculated these numbers back in the day. They just had tables for them. But unfortunately, we have this pesky eccentricity factor, which pops its ugly head in there. And so we would have to create a table for every possible value of eccentricity. And that's just too cumbersome, especially since small variations in E can dramatically change the values of the table. And so we have to find a different approach, or at least Newton did. This was a problem vexing Newton. Remember, Newton's big contribution, the big practical application of the universal gravitation law and so forth, was to be able to predict that the r as a function of t, going from t to r. So be able to predict the motion of Mercury, for example, 20, 50, 100 years in the future, and tell someone in the future where to point their telescope so that they could observe the planets, right? That was the big deal. Or predict when the conjunction of Jupiter and Saturn is, or something like that. Right? So one missing piece of the puzzle to make this an actual practical application, right? We don't often have the question of going from R to T. That's not usually a big deal, or not usually very practical. So Newton's confronted with this nasty problem here, and what does he do? Well, in typical Newtonian fashion, he changes the question, right? And this is how a lot of advancements in technology and science and engineering come about. Instead of saying, well, how can we use existing technology, how can we use existing methods to solve this problem, we invent new methods to solve problems which can't be solved using existing technology. And so one of Newton's great accomplishments, or great contributions to science, is the development of the algorithm. So this is not a simple calculation of given t what is r, or more specifically, given m what is e, but it's a sequence of calculations based on m, which in the limit, as the sequence goes to infinity, for example, right? So m yields a sequence e1, e2, ek, and so forth, so that neither e1 nor e2 nor any ek is a precise value of e, as in it solves this equation. But in the limit, as k goes to infinity, ek is the solution to that equation for a given value of m. So this is a new idea, right? This is a new concept in mathematics, and yet it's, in retrospect, a very prescient one, right? Because, well, I'm sure Newton didn't have any computers used to tabulate, to calculate this sequence, right, of calculations. Perhaps he had postdocs or graduate students who would sit there and do it for him. So if he wanted a particular value of t, or r as a function of t, he could assign that as a homework problem to his students. Of course, right, now we don't have, well, we still have graduate students and postdocs and stuff, but we don't rely on them, and although you will actually on the exam or on the homework to calculate these things by hand. We don't need that. We have computers, right, who do base trivial calculations all the time and do it very fast and much faster than students or postdocs can. And so today, right, we define most of our engineering calculations as the limit of a sequence of calculations. Very few of our results that we find in the literature are, in fact, analytic formulae to solve particular problems. For example, if you want to solve a PDE, well, there are a couple PDEs which have analytic solutions, but very few. You may learn about them when you take a course on PDEs. They'll give you a couple really trivial problems, and they actually have analytic solutions. But this is by far the less common case, the exception rather than the rule. And so to calculate the solution of a PDE, for example, we typically have an initial condition, and we use like a Runge-Kutta method or some kind of numerical integration, which gives us a sequence of numbers or a sequence of calculations, which ultimately yields the solution exactly. Although I guess we could say that actually Kepler came up with numerical integrations to formulate the Rudolphine tables. But actually in this particular problem, of course, that's not necessary. Fortunately for us, the sequence of calculations, the e's that we need to calculate, is not very extensive. We only typically need 3 or 4 iterations to solve this problem. But it's hard to underestimate the impact of the invention of algorithms or iterative methods for calculating the solution to mathematical problems such as this. You might even consider this the birth of numerical methods, or you've taken probably, I know people in 462 have taken a course in numerical methods at some point in their undergraduate career. And in fact, actually, you may have seen Newton iteration before in your in numerical methods class, depending on who's teaching it. In any case, this dramatically increases the set of solvable problems, and in fact, we still do Newton iteration today. It's gradient descent is a variation of scaled Newton iteration, and in fact, actually, in my paper on space elevators, I reduced one of the questions, that a targeting question, find the angle of targeting angle to transfer to the ecliptic plane. It's expressed in terms of Newton iteration. In fact, I brought that up just because I thought it was amusing that still publishing papers on Newton iteration here in my space elevator paper, right? We're using Newton-Raphson iteration. We use a scaled version, but in any case, if you can calculate the derivative of a function analytically And actually, if you can prove that the function itself has nth order derivatives, you can prove that Newton's iteration has quadratic convergence. That means the error decreases quadratically, which is actually very good convergence. And so if you can reduce something to Newton iteration, we can now, at least thanks to Newton, consider that problem to be solved. So that's nice. So let's let's consider this problem, right? So the problem is m equals e minus e sine e. I think that's the one. So that's the problem we want to solve. And how do you think Newton solved this? How do you think he approached this problem? Well, of course, as given E, right? So suppose he's given E and he wants to solve this problem. Well, how would you calculate the solution, right? You're given E, you're given M, and you want to find E. Well, one approach is just to graph the problem. And here I've graphed the mean anomaly as a function of eccentric anomaly. And so you're given a given mean anomaly. Let's say it's 60 degrees, for example. Right there. And we want to find the E, so these lines are different eccentricities. Let's say we're focused on this particular line right here. Okay. So we're given eccentricity, we can plot this line, we can graph it, right, for a given E. So let's say Newton did that, right? And he wanted to determine what this intersection point was, right? Where does mean anomaly equal eccentric anomaly, right? So perhaps, we don't know, right? He looked at his rough plot, and remember, right, he didn't plot it at every point. He plotted a bunch of points, maybe a few points. And he said, well, this point looks pretty close, let's say, this point looks pretty close. I'm going to start at 60 degrees, for example. This point looks pretty close to the line. So he plugs eccentric anomaly into this formula, and he gets a mean anomaly of 30 degrees. So, well, that's not very accurate. So I need this to be more accurate. Because remember, in prediction, right, you want to know where you're pointing your telescope. The predictions have to be very accurate. Because you're off by a couple arc seconds, you're looking into empty space as opposed to finding the asteroid series or something like that. In any case, so you find that point, and, well, it's a little bit off, right? And so the question is which direction to go and how far. So it's a little bit off on the negative side. And I guess Newton's also invented derivatives. So he thought, well, maybe the derivative here is pointing that direction. So I'll go in that direction a little bit so that I'll approximate this function by a line and find where that line intersects. I'll find an analytic expression for that where that line intersects the 60 degree plot. And so he finds that point, and, well, it's actually a little bit off too. So, but it's much more accurate. So I said, no, this is working. It's almost right. So I'll do the same thing again, and he gets another derivative, and it's a little bit closer. And he keeps repeating this a couple times, and hey, that's accurate out to 5 decimal places. So this seems like something that's working in general. And so based on these sequential observations, he proposes a general formulation of how to solve an equation where the expression is differentiable in the variable you're trying to find, right? And so he takes the most general expression for it, because remember, he starts with m equals e minus e sine e. And, well, that's a very specific case, so let's generalize that a little bit by taking a general function, put minus m on e both sides, and saying that general function is e. So specifically, he wants to find the root of an equation of this form as a function of e, right? Or find the e which yields a root of the solution. So he looks at this expression f of e, and he says, well, this is a complicated function with signs and transcendental terms and all sorts of things. And so I don't know how to solve that, right? And he thinks, well, what equations do I know how to solve? Well, I know how to solve linear equations. Well, that's not a linear equation. But then he remembers, well, what is the definition of derivative, right? Well, the derivative is the linear equation, the line, which passes through that point, and in some neighborhood of that point approximates that equation very well, right? So I'll say, well, what is the line that passes through a point in terms of its derivative? And he says, well, I can approximate any function, right, in some neighborhood of that point, say a point k, xk, say by, right, the value of xk, right, so that's the constant, f of xk. So the value of the point, and then plus the slope of that point, right, so the derivative of the function, f prime of xk, so that's the derivative of that at that point. And then, right, the line is, of course, the distance from that point, right? That's the slope times distance, x minus xk. Right? So let's approximate this function, assuming we made a decent initial guess. And he knows how to make decent initial guesses because you could just guess that E is approximately m. So we'll use E1 equals m as our initial guess in this case. So he approximates the function by this line and says, well, I'm going to set that equal to 0. And then I know how to solve that problem, right? Because there's only one variable, it's linear, right? I just move this term to the right-hand side, and so we get divide by the derivative. And okay, there we go. So except now I've got my xk on the wrong side, so I'll just move that over there, plus xk. And hey, there's my solution. I solved this linear expression. So I'm going to take my point. I'm going to approximate the function by a line, hoping that linear approximation is not too bad. And then I'll solve for the root of that equation, this linear expression. And that will give me a point, which is hopefully a reasonable approximation of the solution or the root of the original expression, f of e. And so that's what he does, right? He says, well, that's my next guess for where the solution is going to lie. And so, okay, I make another guess and I check it. And so I check that f of e1. And, well, it's not equal to my desired m. Oops. Well, but it's closer than my original guess. So that's good, right? But closer than, say, e0, which I just guessed as m, for example. And so if it's closer to my point, or my root, then the linear approximation should be a better approximation of the function itself. So I'll just repeat this process. So I'll take, again, this is my new linearization point, x2, right? Or what do I have? x1, x2, right? And I'll repeat this process. So I'll say this x1 is, or xk plus 1 is my new guess. And then x of k plus 2, right? Just repeat xk plus 1 equal minus f of x k plus 1 over f prime of x of k plus 1. Right? And I repeat this, and then I check that value, f of e2, and maybe that's not still equal to m, and so I'll repeat the process, give my f of e3, and that's approximately equal to m, say out to 4 or 5 decimal places, and so I stop. Right? Or maybe if I want to be really accurate, I'll repeat it 4 or 5 times, and because we're now very close to the actual root, the convergence increases. The speed of the convergence increases as we get closer. Right? So this root finding mechanism, right, is a very commonly used form of root finding. Nowadays, we sort of don't use the full derivative. We put a sort of a scaling factor in there because we're less confident. If the derivative is very large, for example, this can send us way off into the distance. And so we put a little scaling factor where the magnitude of rho is less than 1, say 0.01 or 0.1 or something like that. And then we'll have slightly slower convergence, but we get away from problems, which I'll show you on the next slide, where you can get stuck in sort of equilibriums. Yeah. So that's the basic idea behind Newton's algorithm. It's, again, as most algorithms, it's not terribly complicated, right? Here we've got an illustration, a little movie illustrating Newton's algorithm. And here what we see is we have an initial guess. I should put this on repeat. We have an initial guess. We find the derivative of that function at the value of the initial guess. We use that linear approximation to find a new guess for the root. We use that new guess to find a new linear approximation of the function. And we use that to find a new guess, which is hopefully more accurate than the previous one. And we find a new linear approximation, new guess, new linear approximation, new guess, new linear approximation. And as we get closer to the origin, actually, the convergence speeds up quite a bit. You can see that there wasn't much improvement in convergence from x0 to x2 here. But then when we get very close to the origin, right, the convergence from x4 to x5, for example, or x3 to x4, is actually significantly faster. And actually, you can show that, right, this quadratic convergence appears in some neighborhood of the origin. You don't really have an estimate of how close you have to be a priori, but there's some neighborhood where you have quadratic convergence. And you can bound this interval based on the derivatives of the function, how sort of wavy this thing is. So this one's pretty wavy, right, because it's going down and up and down and up and down and up. So it's got how much jiggering you have to do. Of course, in Kepler's equation, there's not the equation is very smooth, right? So we don't have to worry about those jiggers quite so much as we do and in these example functions, right? Because this is a relatively smooth function here. So generally speaking, when Newton's algorithm works, and again, not the scaled Newton's algorithm, but Newton's algorithm works, it works very well. It works very quickly. You only need typically 3 or 4 iterations to get each order of magnitude in accuracy. But that said, and it always converges in some neighborhood of the origin, but that said, there are, it doesn't always work, right? And these are just some illustrations of how it can go wrong. So just be aware. I mean, none of these examples hold in our case, and they don't hold it for particular reasons. So this one particular is not monotone. So it's in Kepler's equation is monotone, so it goes up and keeps going up. This one's not monotone, so it goes up and then comes back down. The problem with that, of course, right? If we're looking for a root. If you do the approximation here, it sends you in the wrong direction. And this one also sends you in the wrong direction. Well, that one sends you in the right direction, but then you get stuck here and it sends you in the wrong direction again. And so you can get in these like loops here. Here's another case where it's not monotone. It's going down and then up again. And it gets stuck at this local minimum here. So you've got, right, you estimate it here. It sends you over here. The derivative sends you over here. You estimate it here. It sends you back over here, right? So of course, if we use the scaled Newton iteration, this repetition wouldn't happen. Essentially, we'd go a little bit, and then it would send us a little bit more this way. And we'd eventually get stuck somewhere here. So we'd have convergence. It just wouldn't be to the correct point. It wouldn't be to the root. But we get stuck at some point. So we'd have convergence, but it wouldn't be to the convergence to the right number. So that's for the scaled iteration. Here's another example of what can go badly wrong. So here's our root that we're looking for. Again, not monotone function. This one is bad in a different way, in that the function is quite high at this point, but the slope is very low at this point. So when you're finding the root, it sends you very far in one direction or another. And that's exacerbated by the fact that here it's sending you in this direction, and here it's sending you this direction. That's because it's not monotone. It's going up here, and it's going down here. Right. So again, not monotone function, and a very weak derivative at a low value is hurting us here. Here's another illustration where it is monotone, but here the problem is a little bit different in that the derivative of the function is actually quite high at the origin and then tapers off. So this is a different kind of problem. So here's our initial guess, for example, here, and this slope is not this slope is low, so it sends us farther out, and then we get another slope, and that sends us even farther out. And as we get farther out, actually the slope is getting smaller, so it's sending us farther and farther out, even though the function itself is monotone. So this one's diverging. This one's not converging, but it could if you use scaled iteration. And at this point, I don't know, maybe this it's not converging, or it's converging to the wrong value or something like that. So there are issues here, right? So if you assume that the function has a bounded derivative and it's convex and various things, you can prove that Newton's iteration works well if you start sufficiently close to the origin, right? And all these things are true, or sorry, the root, I guess. Then all these things are true, then you'll have convergence. But in general, Newton's algorithm doesn't always converge. And of course, he didn't prove any of these things, Newton, but observed that it worked well for his particular problem and probably worked well for other problems. He probably considered it a heuristic, right, not an algorithm. And it is a heuristic in this sense. But it's a heuristic that works very well if certain conditions are satisfied, and they're certainly satisfied for the Kepler equation. Okay. Just scaling scaling's Newton iteration. For Kepler's equation, Newton's iteration just uses no scaling, so it's alpha equal 1. So let's apply this to now Kepler's equation, right? That's Newton's iteration in general, and it's still used to find roots of equations. The particular equation, of course, we're interested in solving is Kepler's equation, which is given here. Right? So this is our function. Let's get rid of the e equals 0 there. And remember what Newton's iteration is, right? So x of k plus 1 equals x of k plus f of xk over f prime of xk. Or is there a negative sign here? I should actually double check that. Minus, yeah, I thought so. Yeah. So there's a minus sign there. So now, in this case, of course, x is e, so e of k plus 1 equals e of k minus f of e of x of k, f of e of k. What is f, right? F is just the Kepler equation, where we've moved m to the left-hand side. Right? Well, actually, we've moved sine e to the right. Instead of moving m to the right-hand side, we've moved it to the left-hand side, but same deal. So we're solving now a ratio here, f, that's m minus e plus e sine e, and put a little k there. M, of course, doesn't change, right? Because we're given m, and we're solving for e. Remember what we're doing. We're given m, we're trying to find e. Right? So that's f of ek. And then, of course, we want the denominator, which is f prime of ek, so we have to figure out what the prime is. So we just take the derivative of this, dE of this whole thing. And, well, dDE of m is 0. dDE of e is 1. Of course, there's a negative sign, so we'll put the negative 1 there. And dDE of this is e cosine e. So the derivative of f with respect to e is f prime equals -1 plus e cosine e. And so we'll just plug that in here to get e cosine ek minus 1. So that's Newton's iteration for eccentric anomaly for solving Kepler's equation given m. So given m, we compute several intermediate steps to get e. So given m, we actually compute e1, then e2, then e3, all the way out to e infinity, in theory, and then that's equal to e. So we could just say equal. Right. So it's an iterative algorithm, right? An update law, and so it's defined recursively. So given an initial e, right, we use that to find e2 by substituting in this equation here. Given e2, we use it to find e3 by substituting in the equation there, and so on and so forth, until we stop. So when do we stop? Well, let me take just a brief pause and say that we have to have some initial guess for e. We have to initialize the algorithm some way. And what shall we choose? Well, the best guess in the majority of cases is just to choose the mean anomaly. We don't really have anything better, right? We could use the first iteration, but hey, that's just the first iteration. So we might as well, because we don't have anything better, just choose the mean anomaly to be our first guess in this iterative process, right? So our first guess is usually just the mean anomaly itself, right? So obviously we can't keep computing these things off to infinity, and so there has to be some stopping criterion, some condition, some accuracy level we're willing to tolerate, or some error level we're willing to tolerate, at which we can stop this iterative process. So if we're doing this by hand, we don't want to go too far, and so we would like to stop when we have that, right, m approximately equals e minus e sine e. And so what's the error in that? Well, it's so we're going to translate that to m minus e minus or plus e sine e magnitude is less than, say, 0.001. 3 decimal places, for example. So of course that's just f of e, right? And so if we plug in ek there, right, ek, we can check the accuracy of that iterate by just computing this value of f, and that'll give us the error in this Kepler's equation, right? And so when that remember, this is in radians, right? Everything is in radians. Always choose, by the way, that's a good reason to choose your initial value as m, because, right, then m is already in radians, presumably, assuming you've calculated it correctly. In any case, right, so that gives us an error on that iterative process in terms of how accurately Kepler's equation is satisfied. Does that tell you how close the actual e is to the true e? Not exactly, but one could find such error estimates, but we don't usually do so. So Newton's iteration is a very fast algorithm. If you wanted to have a better balance between convergence and stability of the algorithm, you use a scaling factor. But for Kepler's equation, it's really not necessary. Just as a brief note before we sort of wrap up here and do a final example, note this is one of the reasons we use mean anomaly is because it behaves slightly better with Kepler's equation. So for example, for large eccentricities, if we look at, say, the solution of true anomaly versus mean anomaly, then there's these derivatives get very large here, or very, very shallow derivatives here. And so the conditioning on Newton's iteration, and in particular the meaning of that error signal, becomes more dubious if we're just looking at the direct relationship between true anomaly and mean anomaly. And of course, mean anomaly is there, a function of time. So it's much easier to go from mean anomaly to eccentric anomaly than go straight from mean anomaly to true anomaly. And that's one of the uses of this algorithm, or one of the reasons why we use eccentric anomaly. All right, so again, it's not terribly complicated, but it is a new concept in that we have to do a sequence of calculations to complete our little diagram now, going from t to m to E1 to E infinity to then f and then to r. Right. So this is the hard problem, right? The easy problem, remember from the previous part of the lecture, was go from r to t. In this case, we're going the hard direction from t to r. All right. So let's give an instance of this problem, right? So suppose we use, say, our angular momentum and energy to find our geometric invariants, A and E. This is, of course, an Earth-centered problem, so I should put a little E there. So one particular point I should mention is assume that this all assumes that the time at 0 corresponds to periapse. So if we go back to our orbit, here's our focus, right? If we're trying to find the position as a function of t, right, we're assuming that t is measured from the periapse, right? Right. If it's not, in a couple slides I'll just tell you what to do if it's not. But at this point, we're assuming that f of t naught is 0. Or actually, we don't have a t naught, so f of 0 is 0. Right, so the problem then is to find the position and velocity, or the radius and velocity, at time 4 hours, right? So after delta t equals 4 hours. Assuming, of course, that t equals 0 is at periapse, right? If we're given an alternative f naught, we'll discuss what to do with that in a second. But right now, we're just assuming measured t naught is periapse. All right. So first step, right, in our sequence, we're given t. First step is to calculate mean anomaly. So to do that, we first calculate mean motion, right? The a factor is in there, so we have to plug in the a. Mu of the Earth is fixed. In this particular case, the mean motion is a very small number, right? It's going to be a very small number in all these cases because it's radians per second, and orbits don't happen in a matter of seconds, right? So it's 1.55 approximately 10 to the negative fourth. We multiply that by time to get the mean anomaly. So time in this case, we have to convert from hours to seconds. So t equals 4 times 60 seconds in a minute times 60 minutes in an hour. So 3600, that's where 3600 comes from. And that gives us the mean anomaly in radians. Now, next step, given mean anomaly, solve for eccentric anomaly. This, of course, is Kepler's problem, or Kepler's equation, and we use Newton iteration to do it. So our initial guess, following my guidance on the previous slide, is to choose E0 or E1 to be the mean anomaly. Again, make sure it's in radians. We then plug it into the Newton iteration formula, and so this is the m, right? This is m. M doesn't change, right? It just gets plugged in. Every Newton iteration is the same. M is the same there, is the same there, is the same there, right? Actually, that one is an error checking, so we should stop that. Here we go. What do we got? This is the eccentricity, right? This is just Kepler's equation. So this is, for our initial guess, this is, we also using mean anomaly, so that's 2.23 in this case. This is also 2.23, so in our first iteration, so we could just, I guess, bring that down there. This is also 2.23. and this is 2.23. And so we have this calculation for our first iteration, and we find that the update from the first to the second iteration is quite substantial, 0.3 radians, 0.35 radians approximately. And well, how accurate is that first guess? Well, let's see how accurately it solves Kepler's equation. And so we plug this into Kepler's equation, which actually I didn't write down anywhere here, which is m equals E minus E sine E. So plug that guess into Kepler's equation and see what kind of error we get from the left to the right-hand side. And the error we get in this case is 0.03. So quite small, actually, compared to the update size, which has been 0.35 radians. But not accurate enough. That's still 0.03 radians approximately. So let's keep going. So we'll take now this value for E2, right? Plug that in for E2 and repeat the process. So plug that in there, plug that in there, plug it in there, plug it in there. And we've got our next iteration just by calculating those numbers. M hasn't changed, it's still the same. E hasn't changed. And we now get another estimate for the eccentric anomaly, which now has only changed by 0.018. So delta E is 0.018. So that's encouraging, right? We're seeing convergence here. It's supposed to 0.35 to 0.018. And so let's now see how accurately this solves Kepler's equation. So let's plug it into Kepler's equation, and we see that the error in Kepler's equation is now 0.00089, so approximately 0.001, which actually, if you remember, my tolerance is below my tolerance. And so technically I could stop here, so let's see if I did. So now we have that the error from iteration 3 is within our tolerance, and so actually we're going to stop now. We're going to set a guess that our eccentric anomaly is 2.57 radians, and we're going to continue with our process now. We've got T, we've got M, we now have approximately E. And now we're just going to go to the final step and get F and R. F comes from the explicit expression we had for F, right? We just plug in for E now directly, and we get that F is approximately 2.861 radians. Now we want to find the position and velocity, so let's plug 2.861 radians into the polar equation, and we get the distance here now, 38,920 kilometers. Well, that's interesting. So that looks like we're sort of somewhere out there on the radian arc. So we're fairly far away at this point, which is not surprising because we're looking at an angle which is somewhat close to pi, right? So pi, remember, occurs at apoapse, and so we're fairly close to pi. So we're on this outward arc of the trajectory, and this is fairly elliptic orbit. It's 0.6 something, so it's not surprising that we're pretty far out there. We can now figure out the velocity just plugging r into this Viva equation, right? We already had a, that was from the previous slide. I forget, what was it? 25,000 kilometers. And we plug it into vis viva, mu of the Earth, and we get a velocity of 2.2 kilometers per second. So a relatively slow-moving orbit at that point. I bet if we calculated velocity here, it would be much faster, but we're not. So we figured out exactly where we're going to be in this orbit. Our true anomaly is 2.861 radians, which is actually, sorry, it's on the other side. So it's up here, right? And our velocity is 2.2. So we've now made a prediction. We can point our telescope at that location, and hopefully we'll observe what it is we're trying to observe. Okay. Now, one last point to keep in mind, and it's a rather important point actually. which is what happens when you're measuring time from not the periapse. So say you're given a position and velocity, and you want to find a future position and velocity, right? Well, okay, so in that case, we have a delta t, right? So that's a problem, because remember our steps are find mean anomaly, eccentric anomaly, true anomaly, yada yada. But we find mean anomaly in terms of absolute time, right? So in this case, what we need to do is calculate what the mean anomaly is by figuring out how far we've progressed, right, in this orbit. So there's a couple different cases. One, you can be given, say, the radius, and we use initial radius, and we use that to find our initial true anomaly. Another case, you're just given the initial true anomaly directly. In any case, you want to calculate your initial true anomaly as your first step, right? So in that case, we need our initial true anomaly, and then we use that to calculate our initial eccentric anomaly using the formula provided. And then we can actually go back through Kepler's equation and find the initial mean anomaly, right? So then, based on the initial mean anomaly, we can find our final mean anomaly by finding the initial one and then figuring out how much time has elapsed since that mean anomaly, right? And this is the mean motion, right? So you can think of delta t. So we had this is a problem, right? We had an initial time, or initial, actually we should say initial true anomaly, for example, or initial radius, and we had to go back E naught, M naught, right? And then we add M naught to this this delta t, and we use it to find the actual mean anomaly of the system, right? Because we can't just calculate mean anomaly. We can calculate change of mean anomaly given change in time, but we can't calculate absolute values of the mean anomaly without knowing the initial value of the mean anomaly. So we have to update our equation a little bit here. Of course, if you start at periapse, then this initial mean anomaly is 0, if f naught equals 0. Right, so, okay, that's pretty much it. A couple warnings, right? First of all, make sure these angles, especially a mean anomaly, can get very large if you do multiple rotations, right? So if you're calculating R and V, for example, you want to limit your mean anomaly to 0 and 2 pi, right? So just if you're larger than 2 pi, subtract off multiples of 2 pi until you're within 2 pi. If you're negative, if you get a negative mean anomaly, add multiples of 2 pi until your interval is between 0 and 2 pi, right? That'll make solving Kepler's equation much, much easier, right? So so just a caveat when solving Kepler's equation, right? Keep your mean anomaly between 0 and 2 pi. I just wrote that down. I don't need to write it again. Also, obviously, don't forget to use radians when solving Kepler's equation. Otherwise, it doesn't work, right? Because remember those geometric calculations, right? One of them required that this angle eccentric anomaly be in radians. So there you go. And a final note, the final warning is if you're given RT naught, remember that generally leads to 2 values of true anomaly. And so when you're going back through from R naught, there are 2 possible values from R naught to M naught. There's 2 possible values of M naught if you're just given R. So you need a little bit more information if you're on the outbound or inbound trajectory. So that could be there or there, remember. All right. So other than those warnings, right, those are the things that people mess up most often. So just I thought I'd write them down on the slide. Other than that, the process is relatively straightforward. It's just this this going from mean anomaly to eccentric anomaly requires a couple iterations. And so finally, we can conclude, right, our progression T to M to E to f to r and v. Right? We can do the hard way, and of course we can reverse these steps and go the easier way. It's just when you're going this way, you need a couple iterations, E1, E2, E3. Okay. So that concludes this part B of the lecture. We now have done most of the things we're going to do in 2D. In lecture 5, we will repeat this lecture essentially, relatively briefly, for hyperbolic anomaly. For this lecture 4 only applies to ellipses. In lecture 5, we'll consider the same thing for hyperbolic anomaly, but it will more or less be a repeat. No big additional concepts other than hyperbolic anomaly itself. Right? Eccentric anomaly, obviously undefined. There's no inscribing circle or anything like that. So with that, I will conclude this lecture, and I will see you all in lecture 5, where we'll do the same thing again for hyperbole.